All right, here we want to look at spherical coordinates. So this was problem 6 on the homework. And this one says the position of any point. Yeah, we're going to read all that. So you guys have read the problem. I've circled in red the questions. I guess first of all, let's look at this spherical coordinate. So here is the point that we're looking at. That's r is equal to x, y, z. And if I project straight down from that point, I will end up on that black line, and that makes a right angle here. Okay, so with spherical coordinates, the first thing we can imagine setting is the radius, and that basically creates a sphere. And then we can imagine setting the angle phi. Hey now, I'm not trying to move that, I'm trying to draw on it. Setting an angle phi along, the same way we defined phi for polar coordinates. And what that does is it creates an arc on that sphere. Everything on this arc has the same r and the same phi. Okay, and you can imagine as we change phi, we would change where that arc ends up on the sphere. And then theta says, all right, we're going to start at the z-axis and we're going to move along that arc until we've covered an angle theta, and that's the point we end up at. Okay, so those are how r, theta, and phi are defined in spherical coordinates. First question says, write x, y, and z in terms of r, theta, and phi. Okay, so let me redraw some of what I just erased. We're going to drop straight down from our point to this line. That's in the xy plane. And so this point down here is going to have coordinates x comma y. And I can imagine drawing a triangle here where this is a right triangle. Let me zoom in a little bit. And the x coordinate goes from the axis or from the origin to here. So that's going to tell me my x coordinate. And then my y coordinate goes along here. So here's x and here's y. And this angle in here is phi. And this angle is theta. This distance is r. So on this vertical triangle, the base of the vertical triangle is r sine theta, and the base of the vertical triangle is the hypotenuse of the flat triangle in the xy plane. So, based on that, x is going to equal the hypotenuse of that bottom triangle, r sine theta, times cosine of the angle in the flat triangle, so cosine phi. Y is going to equal r sine theta, sine theta. That is the hypotenuse of this flat triangle, times, since it's the opposite, it's going to be sine of phi. And z, okay, where's z? Z is the height of this vertical triangle. So since this is my angle theta, by the way, how do I know that was my angle theta? This is my angle theta down here. If this dotted line is a vertical line and the z-axis is a vertical line, these are opposite interior angles between parallel lines, and so they have to be the same angle. So that angle theta here at the top of this triangle and this angle theta here at the bottom have to be equal to each other. Okay. So, right, and this distance from the origin, like this is a rectangle here. And so the height of that rectangle is z. And if I go back to looking at just this red triangle here, this vertical triangle, z will be equal to the hypotenuse, which is r, times the cosine of theta, because it's the adjacent side. Okay, and of course we can look those up. Anywhere you go, you can look up x, y, and z in spherical coordinates, as long as the spherical coordinates are defined the same way that we've defined them here. But being able to draw it on this picture really helps. X, y, and z in terms of r, theta, and phi. Describe the three unit vectors, r hat, theta hat, and phi hat. And again, in words, I'm just going to say, hey, they point in the direction of increasing r, they point in the direction of increasing theta, and they point in the direction of increasing phi. But let's try to draw those on this picture. So increasing r means the point would be moving radially outward along this line. So the r hat vector would be pointing radially outward along that line. Increasing phi, what we can imagine is that there is a circle on the sphere with constant height, with a constant z. Increasing phi is going to point a tangent along that circle. Okay, and I just put that right where I need to draw the next one. So let's call this one phi hat. Let's move this r hat label. Okay, so my vector points tangent to that circle. The r hat vector points outward from the sphere. And the theta hat vector is going to point along the circle that's already on here. It's going to point tangent to the circle this way. So this is going to be my theta hat. And right, the one that points outward from the sphere is my r hat. So how would I say this? I don't know. I don't know how to, I mean, if I just wanted to write it in a simple sentence, the direction of increasing r, the direction of increasing phi, and the direction of increasing theta. But I think, again, getting them on the picture really helps. And understanding those three directions are all mutually perpendicular to each other is also interesting. Okay, but now we need to write the directions. R hat, I think we're going to have to write the directions because we've described the unit vectors, but we need to write an expression. We need to differentiate r hat, theta hat, and phi hat. Before we do that, the next thing that we are asked to do is write the r vector in terms of, we're supposed to write it in terms of r, theta, phi, and r hat, and theta hat, and phi hat. And this one's just really super simple. If we have a unit vector that points, if the r hat unit vector points along this radius, if I just take r of them, like if r is 6, I just take 6 of those and add them together, I end up exactly where I'm supposed to be. So this is just r times r hat. And that's it, we're done. All of the dependence in theta and phi is contained within the r hat vector. The r hat vector will change if theta changes. The r hat vector will change if phi changes. So all of the dependence on theta and phi is contained within that vector, that little r hat vector. So this is it. This is my r vector in terms of r, theta, phi, r hat, theta, hat, and phi hat. Okay. So the next thing we need to do is write down expressions for r hat, theta hat, and phi hat. I guess I'll do it in the other order. R hat, phi hat, and theta hat. Okay. Well, so to find r hat, the easiest way to do that is probably to do the r vector divided by the length of the r vector. And the r vector is x hat plus y hat plus z hat. Hope that makes sense. So I'll go ahead and write it down. X hat, so this is going to be r sine theta cosine phi x hat plus r sine theta sine phi y hat, and of course I ran out of room. Plus r cosine theta z hat, all of that divided by r, and the r's cancel, and we get our expression for r hat. R hat is equal to sine theta cosine phi x hat plus sine theta sine phi y hat plus cosine theta z hat. I'll go ahead and put a box around that. Seems like it's going to be important. Okay, that was the easy one. So, ooh, yikes. Oh, goodness. Oh. Oh. Okay. I don't like that disappeared, but whatever. Oh, okay. Well, fair enough. Okie doke, where are we now? We are trying to find phi hat. So phi hat, I said there is a circle at constant z on the sphere, and phi hat points in the direction of increasing phi hat is going to point in the direction of increasing phi along that circle. First thing I notice is no z hat component. Okay? So it's just going to have x hat and y hat. It's parallel to the xy plane. Okay, great. It also doesn't depend on theta. If I was down here with a different theta, my phi hat would be pointing in the same direction. So phi hat does not depend on theta. Okay. Also, phi hat is a unit vector. So it's going to have, the easiest way to make a unit vector is to have sines and cosines. So the easiest thing to guess is something like sine phi x hat plus cosine phi y hat. But I want to make sure I get them right because when phi is equal to 0, oh look, this is actually going to be exactly the same as cylindrical coordinates. When phi is equal to 0, we point in the y-hat direction, which means we should have a cosine phi y-hat. And when sine is equal to 90 degrees, when phi is equal to 90 degrees, we get a negative x-hat, so minus sine phi. That didn't help me. Minus sine phi x-hat plus cosine phi y-hat. And I think that's the same phi hat as cylindrical coordinates, which does make sense. Okay, and now theta hat is going to point, no, I've already, let's use purple. Theta hat is going to point in the direction of increasing theta along that line, and looks like theta hat will depend on theta and phi. It'll change directions when theta changes directions. It'll change directions when phi changes directions. Let's see. With respect to theta, when theta is 0, when theta is 0, the z component of theta hat is 0. So that sounds like sine theta z hat. When theta is 90 degrees, the z component points straight down. Okay, so that actually sounds like minus sine theta z hat. And it doesn't look like the z component depends on phi much, because it's going to point straight down regardless of what the angle phi is. So that means that we're going to have cos theta for both of the other terms. Okay, so if I project this down onto the line below it, where did my purple go? Oh, purple. Oh, I see. Okay, if I project this down onto the line below it, we can see that if I project this down onto the line below it, this thing has a length of cosine theta. And how do I know that? Because this angle here did I get that wrong? No. Okay. 0 degrees. Okay. Nope. So this angle is theta, which means this angle is 90 minus theta, which means the opposite side of that triangle is going to be cosine theta. Okay, right. Ah! No! Okay, good. Okay. So this little line has a length of cosine theta, and it has an x component and a y component. Where's the angle phi in there? Well, this one's 90 minus phi, so I guess that's 90 minus phi. Okay, which means the x component is the opposite of 90 minus phi, so the x component is going to be cosine phi. Okay, and I think those are our 3 unit vectors. Now, I feel like I did a really good job deriving those, looking at the pictures and seeing where all those came from. But I do want to check my notes, so if you'll bear with me for just a second. I've been doing this without a net, so to speak, not checking my notes. So let me sort of double check and make sure I agree with me that r hat is sine theta cosine phi, x hat sine theta sine phi, y hat cosine theta z hat, theta hat is cos theta cos phi I hat cos theta sine phi j hat minus sine theta z hat, and phi is minus sine phi x hat plus cosine phi j hat. And here's an interesting fact. I will let you check this for yourself. I won't try to prove it here. Phi hat is equal to r hat cross theta hat. Just like z hat is equal to I hat cross, x hat cross y hat. The 3 unit vectors are mutually perpendicular to each other, and in a right-handed coordinate system, x cross y is always equal to z, and r cross theta is always equal to phi. So that's interesting, and you can prove that by taking this cross product if you want to. Okay, all of that was just so that we could get r hat dot, phi hat dot, and theta hat dot. We need the time derivatives of these unit vectors. And as you can imagine, this is going to get tedious and ugly because we've got lots of chain rules here, or lots of product rules. So for the r hat vector, I've got cosine theta, theta dot, cosine phi x hat plus, well, let's hold off on the x hat, plus sine theta minus sine phi dot. So first I took the derivative of the sine term, and I got cosine theta dot, multiplied it by cos phi. Then I took the derivative of the cosine term, I kept my sine theta, and I got minus sine phi dot. And so both of those are in the x hat direction, plus in the y hat direction, taking the derivative of the sine first, I get cosine theta dot sine phi. Then taking the derivative of the sine phi, I get plus sine theta cosine phi dot, and all of that is in the y hat direction. And then in the z hat direction, I get minus sine theta dot. So what I'm going to do is group these in terms of the phi dot and the theta dot. So let's get a new page. So r hat dot is going to be equal to theta dot times, and for theta dot, we're going to be looking at this term, and this term. Okay, so that's going to be cos theta cos phi x hat plus cos theta sine phi y hat minus sine theta z hat, okay, plus phi dot times, and for the phi dot, we're going to be looking at this term and this term. So phi dot times negative sine theta sine phi x hat plus sine theta cosine phi y hat. Okay, so r hat dot is equal to theta dot times this thing in brackets. But that thing in brackets is theta hat. So theta dot theta hat plus phi dot times the thing in brackets here, and the thing in brackets there is, interesting, it's equal to sine theta times phi dot, or phi hat. So if I pull out the sine theta, I get a sine theta out here, and then this goes away, and this goes away. And I get minus sine phi x hat cosine phi y hat, which is theta or phi hat. So let's put a box around this. Looks important. This is r hat dot. That is how r hat changes with time. And r hat will change if and only if either theta or phi are changing. Okay, so that seems okay. Phi, or let's do theta. Theta hat dot is equal to, let's look at our theta hat up there. So again, got to do my product rules. So I'm going to get cosine, I'm taking the derivative of cosine theta. So this is going to be negative sine theta, theta dot, cosine phi, minus cos theta sine phi, phi dot, and all of that is in the x hat direction. So plus negative sine theta, theta dot, sine phi, plus cosine theta, cosine phi, phi dot, and all of that is in the y hat direction, plus in the z hat direction, we get minus cosine theta, theta dot z hat. Okay, and like we did before, we're going to collect these terms in terms of theta dot and phi dot. So this is going to be equal to theta dot times, well, can we do this in our heads? So the terms we're looking at for theta dot are this term, and this term. So once we pull out the theta dot, we'll have minus sine phi sine theta cosine phi minus sine theta sine phi minus cosine theta x, y, and z, and we can see that that is exactly negative r hat. So it looks like this is minus theta dot r hat. And then if we look at the terms with phi dot, and we pull out a phi dot cosine theta, we're left with minus sine phi x hat cosine phi y hat, which is exactly phi hat. Okay. Okay, so we've got our hat dot. Let's go ahead and put a box around that one. Lastly, let's look at phi hat dot. So let me bring that back down here. So phi hat is equal to minus sine phi x hat plus cos phi y hat. Okay. So we need phi hat dot. Phi hat dot is equal to minus sine phi dot x hat. Nope. Derivative of sine is cosine, so minus cosine phi dot, minus derivative of cosine is negative sine phi dot y hat. So phi dot hat is equal to phi dot times times what? That's not phi hat. So okay, this is embarrassing. I gotta check my notes again. Been a little while since I've been through this. make sure that I got phi hat right. Phi hat is negative sine phi I hat plus cosine phi y hat. So phi hat dot okay. Let's say that phi hat dot is that. Yeah, that's what I thought. Okay. Okay. Yeah. All right. Yep. This is really nasty. Okay. So it's phi hat dot times minus cos phi x hat minus sine phi y hat. Which it would be nice if that was just phi hat, but it's not. It's, they're in the wrong order and they're both negative, and so it's just not. So we're going to have to somehow write this in terms of r hat and theta hat. So what I'm going to do, I want to end up with just cos phi. And these both have cos phi in them. And I want to end up with just sine phi. And these both have sine phi in them. So it looks like sine theta r hat. Let me write down sine theta r hat plus cosine theta hat. Now, why would I do that? Well, because r hat has sine theta in it. And if I multiply it by sine theta, I'm going to get up with sine theta squared. Theta hat has cosine theta in it. If I multiply it by cosine theta, I'm going to end up with cosine theta squared. And then if I add them together, I'm going to have a sine theta plus cosine theta that's going to add up to 1. So this might work. Okay. So I need sine theta times this plus cosine theta times that. To help me out, I'm going to duplicate the, fine. I'm going to duplicate this, and, I can't bring it to a new page. Fine. Can I paste it? Okay, that worked. Okay, bear with me. Okay, paste, nope. Got. Oh, fine, I'll just rewrite it. Okay, let's rewrite r hat and theta hat. So r hat, so this is going to be sine theta times r hat, which is sine theta cosine phi x hat plus sine theta sine phi y hat plus cos theta z hat plus cosine theta hat, and theta hat is cosine theta cosine phi x hat plus cosine theta sine phi y hat plus sine theta z hat. Okay, so when I add those together, or when I multiply this out, this is going to give me sine squared, sine cosine. This is going to give me cosine squared, sine cosine. And importantly, this was minus sine theta. Okay, so when I add these two together, in the x hat direction, I've got sine squared cos phi plus cosine squared cos phi, which is sine squared plus cosine squared times cos phi, which is just cos phi. In the y direction, I have sine squared sine phi plus cosine squared sine phi, which is sine squared plus cosine squared sine phi, which is just sine phi. And in the z hat direction, I've got sine theta cosine theta minus sine theta cosine theta. So that's just 0. So it looks like sine theta r hat plus cosine theta theta hat is equal to cos phi x hat plus sine phi y hat Okay, so that gives me phi hat dot is equal to negative phi dot times times sine theta r hat plus cos theta theta hat. And that looks important, so let's put a box around it. So now I have my three derivatives, r hat dot, theta hat dot, phi hat dot. So now, finally, I can start taking derivatives of the r vector. The r vector is equal to r times r hat. So the velocity vector is going to be equal to r dot times r hat plus r times r hat dot. So the velocity vector is going to be equal to r dot r hat. That is the speed with which r is increasing in the r hat direction, which makes perfect sense. That's what any of us would have guessed. If r increased, that there'd be a velocity component in the r hat direction, plus r times the r hat dot vector, which is this guy. Okay, so V is equal to r dot r hat plus r theta dot theta hat plus r sine theta phi dot phi hat. Okay, so let's talk about this. It makes sense that if r is increasing, you're going to have a component of the velocity in the r hat direction. Great. It makes sense that if theta is increasing, you're going to have a velocity in the theta hat direction. Great. Now, it's not just equal to theta dot theta hat, as you might expect, for a couple of reasons. First of all, that wouldn't have the right units, because velocity has to be meters per second, and theta dot's just per second. So r times theta dot gives us meters per second. But again, as we have discussed before, this is basically r omega. And if you're moving along a circle, velocity is equal to r omega. So that makes perfect sense. Okay, what about in the phi direction? Again, it makes sense that if phi is increasing, there's going to be a velocity in the phi hat direction. And it makes sense that we need to multiply by a distance, but why r sine theta? Well, if we go back up to here, the radius of this circle, is r sine theta. And so when we're moving along that circle, we're moving around a smaller circle than if we're moving around this circle. So when theta is increasing, we're moving along a circumference of the sphere. But when phi is increasing, we're not moving around a circumference of the big sphere. In fact, the smaller theta is, the smaller the circle is we're moving around. So r sine theta is the radius of the circle that we're moving around, and this is still just r omega, where omega tells us how quickly the angle is changing, and r is the radius of the circle that we're moving around. So in fact, we could have written this, if we were really clever people, we could have written this velocity just from first principles, just from our physics 1 understanding of if the angle is changing, the velocity is going to be r times omega along that circle. Okay, well that was the easy one. Now we need to find the acceleration vector. So to find the acceleration vector, we need some product rules here. So the first one's going to have two terms. That's going to be r double dot times r hat, so the derivative of the first times the second, plus r dot times r hat dot, the first times the derivative of the second. The next one's going to have three terms, r hat, theta hat, r dot, theta hat, that's the derivative of the first one, plus the derivative of the second one, r theta double dot, theta hat, plus the derivative of the third one, r theta dot, theta hat dot. Okay, and then the last one is going to have four terms, plus r dot sine theta phi dot phi hat, plus r, derivative of sine is cosine, cosine theta, theta dot phi hat, plus r sine theta phi double dot phi hat, plus r sine theta phi dot phi hat dot. Oh, for the love of Pete. 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, none of which just immediately cancel. And most of which, or many of which, we have to deal with. So the ones we have to deal with have the derivatives of the unit vectors. These three are a problem for us. So those three we're going to have to plug in these unit vectors for. Okay, so tedious, but not hard. A vector is equal to r double dot r hat plus r dot times And now we need r hat dot, which is this guy. Oops. Plus cut paste. Okay, plus r dot theta hat plus r theta double dot theta hat plus r theta dot times, now I need my my theta hat dot. So that's this guy. Oopsie. Plus cut, paste, okay, plus r dot sine theta phi dot phi hat plus r cosine theta theta dot phi hat plus r sine theta phi double dot phi hat plus r sine theta phi dot times phi dot hat, which is this guy. Plus cut, paste. Okay, let's shrink it a little bit and paste it here. And we can move that negative sign out to the front. And let's see, this becomes phi dot squared. And then I can move this in a little closer. And that is my A vector. So let's keep going. A vector. Now we just need to collect like terms. So I want everything with r hat in it. So we've got an r double dot, which means that if the circle is accelerating outward, the particle will have an acceleration that points outward, which makes perfect sense. That may be the only one that makes perfect sense. Okay, let's see. So we just took care of that. The next one with r hat in it is this one. It's going to be minus r it was this term right here, minus r theta dot squared. Okay, minus r theta dot squared. So we just got rid of that term. The next term that has r hat in it, yes, is a minus r sine squared theta phi dot squared, r sine squared theta phi dot squared. Yep, okay, and that got rid of that term. Plus theta hat times, okay, and we've got an r dot theta hat here, and we've got another r dot theta hat here, so we've got 2 r dot theta dot. We've got an r theta double dot plus r theta double dot. That's phi hat, that's phi hat, that's phi hat, that's phi hat. Okay, and then we've got an r, a minus r sine theta, cosine theta, r sine theta, cosine theta, phi dot squared okay, plus in the phi hat direction. Let's see, so I just got rid of that one. So everything that's left should be in the phi hat direction. I have an r dot theta dot sine theta, and I've got another I've got an r dot phi dot sine theta, r dot phi dot sine theta here. I've got another r dot phi dot sine theta here, so that is going to give me a 2 r dot phi dot sine theta. Yep, r dot phi dot sine theta. Good. Okay. So now this whole thing is taken care of. I've got an r theta dot phi dot cosine theta plus r cos theta theta dot phi dot. That took care of this term, which took care of that whole thing. Here's another r cos theta theta dot phi dot, this term here, which means I have 2 of those. Let me fix that. And then we've got an r sine theta phi double dot. Which takes care of that one. And we've got a minus r sine theta phi dot squared. No, we don't. This term was already taken care of. Good. I was wondering where that was going. Okay, cool. In cylindrical coordinates, we were able to make some sense of this acceleration. Let's see if we can make any sense of this one. So this is the acceleration because the sphere is getting bigger. There's an outward acceleration if the sphere is accelerating outward. Okay? This one is the centripetal acceleration of the object going around this circle. So if the object's going around this circle, there's an acceleration that points toward the center of the circle. It points in the negative r hat direction. Okay, this one is part of the centripetal acceleration, r omega squared, of the particle going around this circle. If the particle goes around this circle, there's an acceleration. If the particle is going around this circle, there's an acceleration that points inward. And that acceleration has an r component and it might have an r component, a theta component, and a phi component. Let's see. That centripetal acceleration has an r component, So we're looking for, it has a theta component. It does not look like it has a phi component. So the centripetal acceleration of going around the small circle points both in the r direction and in the theta direction. So this is a centripetal acceleration. So this is a centripetal acceleration for going around the big circle. These two together are the centripetal acceleration going around the small circle. This is the radial acceleration. Okay. This term is my r alpha for accelerating along the theta direction. If you're accelerating along the theta direction, there should be an acceleration in the theta direction. That makes sense. This is, again, my Coriolis term, which, again, we'll talk about Coriolis in a future chapter. It's real, but it's confusing. So then let's look at these last terms. Okay, this is also a Coriolis term. This is also a Coriolis term. Notice that they both have r dot theta dot, r dot phi dot, and then this one's a theta dot phi dot, which is a really interesting term. And then this one is the easy to understand term. It says that if there is an acceleration of phi, remember on my sphere, that's the small circle up here, so the particle is accelerating along that small circle. There will be an acceleration that points along that small circle, which is the phi hat direction. Okay, so this is acceleration in spherical coordinates. Yeah, so if I do F equals ma in spherical coordinates, and I know that, for example, my force is equal to 3 newtons r hat plus 7 newtons phi hat, for example, when I plug that into ma, I've got to use this acceleration because I'm doing F equals ma in polar coordinates, for example. So then that's going to give me several differential equations for r, theta, and phi. And you can imagine that those would be incredibly ugly. And we can get those differential equations, but usually we're going to have to solve them numerically, because once I get that differential equation, it's going to be not one that we can usually solve analytically unless it's a very simple situation. Okay, that is the end of spherical coordinates.